All right, well, let's get started. First of all, thanks to everyone for sharing at least part of your lunch hour with us today. We're going to go into a deep dive of Amazon Neptune. But before we do, how many of you watched the keynote this morning? Yeah, so really exciting day for AWS Database Services with the announcement of Amazon Quantum Ledger Database as well as Amazon TimeStream. It was really just a year ago that we were in the similar boat, announced as a preview service in Andy's keynote. So understand exactly what that means. But how many of you today are using a graph database? OK, fantastic. How many of you are using Property Graph and Apache Tinkerpop? A few. How many of you are using RDF-SPARQL? A few as well. And then the tough question, how many of you are using Amazon Neptune already? OK, fantastic, fantastic. So we are going to have some time at the end for questions. So please feel free to ask us your deepest, darkest questions about Neptune, and we'll do our best to answer them. So, but with that, why don't we go ahead and get started? So we're going to cover a little bit of an overview about building applications and the different types of graph models and some of the characteristics of Neptune. And then my colleague, Bruce McGowie, is going to go into the details of our underlying storage layer. So what is it behind Neptune that gives us the features for enterprise availability and scalability? If you're interested in learning more about graphs or about Amazon Neptune, there are other opportunities here at reInvent. And so we have some things that are more hands-on in terms of looking at specific performance tuning pieces. So folks that are using Neptune today, you might really benefit from that session. Some of our engineers are there. They can walk you through some of the things that we've learned about how to get the best performance out of Neptune and the various clients that we have. And then we also have other options to get started with Neptune. So definitely plenty of things to learn. But this kind of where we start off is, what kinds of applications can benefit from a graph database? And the answer is relatively simple at first. It's graph databases are really when you want to traverse relationships. And if this is what is the primary data access pattern in your application, then a graph database is something that you may want to consider. The kinds of data that we see, which we think of as rich and highly connected, is characterized by lots of different things. It comes from many different sources. It's produced at different rates. It's heterogeneous in terms of the schema and the formats. But the thing that unites all of these use cases is that the real value that you get in the applications is thinking about the relationships. And there's lots and lots of different use cases for connected data. When we launched Neptune, we expected customers to build social networking applications, to use graphs to model how people interact. We expected people to build recommendation engines to look at how they can provide in-game offers or product recommendations in their applications as part of their user experience. And we expected people to build fraud applications to help understand what are the attributes across different accounts and different transactions that may be indicative of patterns of fraud. But an interesting thing happens when you build a purpose-built database and give developers a high-performance tool for specialized types of database applications, is that they start to discover and do really interesting and exciting things with it. So yes, we do have customers in production with Neptune for their social networks. There's actually a Nike session that's going to start in a few minutes talking about how Nike's migrating their social platform to use Neptune underneath. And we have customers that are using Neptune to make recommendations and to build recommendation engines as well as fraud. But we've also seen customers use graph as a technique to take on other types of problems, things that are more strategic to their businesses, to allow them to make connections between data sets that they haven't been able to connect previously. And so we've also seen customers build knowledge graph applications to help people find and retrieve information to be able to answer new questions. Customers are using it in the life sciences to discover new treatments for existing approved drugs, or also to look at how to bring different medical record systems and hospital systems together to give treatment practitioners a common view of their data. And of course, network security as well. So lots and lots of different use cases. Let me walk through a couple of examples of how you can use these techniques. So if we start with a simple social network here, we can see we have Bill, and Bill knows Alice and Bob. But we also have some other data in our organization that we want to bring to bear. We also have product purchase history. So we can see what these users purchased. We have someone else as well. And in addition to that, we have some shared interest information. So we understand what these users have expressed as their interests. And by using a technique that we call triadic closure, a triangle is the smallest fully connected subgraph in a graph, we can identify new edges that would create triangles. And this is the basis for the start of a recommendation algorithm. So by adding an edge between Sarah and product, we can make a recommendation that Sarah may want to purchase this product because people who also were interested in sports purchased that product. And again, on the right-hand side, you can see that there's an individual, Bill, who has two friends in common, but there's not yet an edge connecting them. So we can also use the same technique to make a recommendation. Sometimes you want to help people find things, to answer more sophisticated questions. And knowledge graphs are a technique that you can use to do that. A knowledge graph uses a graph model to encode domain information and to link together different sets of source data, and that allows you to traverse that to answer questions. So here we start with an example that's taken from the World Wide Web Consortium, or the W3C's primer on knowledge graphs. And it has a very famous piece of artwork, the Mona Lisa, very famous artist, Leonardo da Vinci, and where it's located. But we're also going to add some other information. So we're going to add some social network information. So here we have some shared interests. Again, we have friendship connections. And then we're also going to add information about geographic references and travel type data. And so now we can see where this museum is located. We can see where these individuals have traveled. And that gives us the basis to start to answer more sophisticated questions. So we can now answer questions like, who painted the Mona Lisa? Or what museum should Alice visit while in Paris? Or what other artists have paintings in the Louvre? So knowledge graphs, another example of a powerful technique to use graphs to build applications. One of our public reference customers, is there anyone here from Thomson Reuters in the audience? No. So Thomson Reuters is one of our Neptune reference customers. And they have a number of different graph use cases. This one is very interesting. What they've done is they've created a new service for their customers. They have used a graph model to model global tax policies and compliance regulations. And then they've also used a graph model to represent their customers' corporate and legal entities. And by combining these, they're able to offer a new service that helps their customers both understand what their tax obligations are for a given operating structure, and then as a second order, to help them understand how they might be able to optimize their entity structures in that regards. And these kinds of tax and reg tech use cases also show up relatively frequently in the graph space, where people are looking at using the power of graphs and the relationships to help them reduce their cost of regulatory compliance. So when we started on the journey of building Neptune, we really started by asking ourselves, what are the options that customers have to process this kind of connected data? And the natural first question is, can I use a relational database to process this? The answer is yes, absolutely you can. But there's a couple of drawbacks. And what we found is that the drawbacks are the way that you express traversals or graph patterns over a relational database is in SQL and using SQL joins. And for even relatively simple graph patterns or joins, they quickly become complex SQL queries. The types of I/O workloads that graph databases have are very, very different than what you see in relational databases. So these kinds of join queries will run very slowly on relational databases. And as a result, when you build graph applications on a relational database, you spend a lot of time tuning and denormalizing your data model to get good traversal performance out of it. And so that means that as a developer, as someone building a graph application using a relational database, it's much slower for you to do that because every time you want to add a new relationship or express a new traversal, you potentially have to change your data model to do so. You can also look at this same question from a data model perspective. So on your left-hand side, you can see a notional entity relationship diagram of an HR system. And it has lots of really great data in it. It has relationships between employees and departments and other HR information. And it works really well for the application that it's intended to serve, which is to build HR or to do HR processes. But if you want to use that information to answer other questions, suppose you wanted to say, well, what skills do employees need to have to build a particular product? It would be very difficult for you to do that because the answers are really trapped in that relational schema. So on your right-hand side, you can see a notional graph model. And what immediately jumps out is that the relationships become first-class objects in a graph data model. And that means that you can very easily and directly address them and query them. And that's really the power of a graph database. So graph databases are both optimized for the kinds of I/O workloads that are common for graph processing, as well as supporting graph query languages and APIs that make it efficient, effective, and concise for you to express these traversals and to build applications over them. Now, there's two major graph models and frameworks. And if there's really one important message about graph models that I'd like for you to take home today, it's that it's all graph. Really, so there's property graph, and property graphs consist of nodes and node properties and edges and edge properties. And the leading framework for property graphs in open source is something called Apache Tinkerpop. Apache Tinkerpop provides an imperative traversal language, which is called Gremlin, that allows you to express graph traversals and graph patterns over property graphs. And the second model is something that's a standard from the W3C, which is called the Resource Description Framework, which expresses a graph model. And the Resource Description Framework, or RDF, has a declarative graph query language, which is called GeoSparkl, that allows you to write graph queries over RDF graphs. So back to it's just graph. So customers often ask us, which model is right for which application. And the answer is really, there are some differences, particularly in the way the syntax for edge properties in property graph versus RDF uses something called reification to express them. But conceptually, you can implement almost any application with either model. What we do find is that if you're coming from a relational database background into the graph space, it's often a more straightforward transition, or you find it easier to move from thinking about rows and tables to thinking about nodes and node properties and edge properties. Also, if your application itself, as a user interacts with it, they're building a graph traversal. So if you think about a social networking application, someone selects an interest in a friend, and that's basically traversing out an edge and making another traversal. The imperative nature of Gremlin can be a really natural fit for those kinds of applications. On the other hand, RDF was originally defined to describe resources on the web. And so if you've ever looked at RDF, you'll see lots of things that look like URLs inside of them. They're actually called Internationalized Resource Identifiers, or IRIs. And they give RDF a very strong sense of identity. So RDF carries this background with it. And it also has standardized data serialization formats. So there's lots of data sets that are publicly available from sources like open government data, life sciences data. There's things, Wikidata, for example, has an RDF version. And so if your application uses these kinds of data sets to help bootstrap it or as part of its processing, RDF can be a very natural fit. And in addition, because of its history as describing web resources, there's lots of different language features and supporting standards for RDF, such that if your application is focused on data canonicalization or building common data models from multiple sources, there's lots of different features that enable you to do that. So different models, different strengths, all graph. So let's look at a particular example. Now, you're not really intended to make any sense of this diagram other than to say that this is a structure from something called the Lehigh University benchmark, which is the oldest and most well-known graph benchmark. And it consists of a simulated university system where universities have professors and students take courses, and there's graduate students, and so on and so forth. And you'll also see on your left-hand side sort of a blowout of what the professor graph hierarchy looks like. And so we're going to look at an example here. And so there's actually 14 different queries in the Lehigh University benchmark. This, if you're familiar with it, this happens to be Lubum query number 2. It asks the question, it's a conjunctive join query. It asks the question, find all the graduate students who received an undergraduate degree from the same university. And if we want to think about this conceptually, this is how it would look as a query. So we start with the graduate students. We find where they're members of departments. We find the organizations, the universities that those departments belong to. And then we find the graduate students that also have edges to those universities. So that's conceptually how we want to approach this query. Now, we can look at it in Gremlin. Now, you recall that Gremlin is an imperative language. So at the top, the g.v is basically saying, start with my whole graph and find me vertices that have the label graduate student. And then store them off in effectively a temporary variable, so this as student construct. Now that we've found all the graduate students, we're going to start our traversal. So we go on the outbound edges for the graduate students to find all of the universities. Then we traverse the incoming edges to find the departments that are part of those universities. And then we go back out to find all of the graduate students that are members of the department. And on the last step, we effectively take the intersection of what we started with, all of the graduate students in the graph, with all of the graduate students that we found from the universities. And that's how we would evaluate this query in Gremlin. Now, SPARKL is a declarative graph query language. So if you're familiar with SQL, SPARKL will look a little bit familiar. Across the top, you'll see those IRIs that I mentioned. These are namespaces, and so this is giving the data a strong sense of identity. And then we start in our select statement. The first 3 lines inside below the where are essentially binding variables, which are start with a question mark in SPARKL, to graduate students, to universities, and to departments. And then we start our conjunctive join. So we find where the students are members of the departments, where the departments are organizations of the university, and where the students have a university degree, have a degree from that university. So same question, very different way to express the answer. So the second thing that we did from a product perspective is we looked at what are the options that customers have to use a graph database. And one of the things that really struck us is that we talked to lots of customers that had done a very successful proof of concept or prototype with the graph database. And they found that the languages were natural. They liked the way that you could think about expressing a problem in a graph structure. But when they tried to take these proofs of concepts from a POC status into production, they started to encounter some challenges. And the kinds of challenges that they found were that they spent a lot of time trying to maintain query performance as the data scale increased. So it was very hard to do that. That caused a very high ops workload. And then as they wanted to get enterprise features like high availability, read replication, or encryption at rest, what they found is that these features were not available in community or open source editions, and they needed to have enterprise licensing, which was relatively expensive. And then finally, while there are alternatives that support both the RDF and the property graph models, there tends to be a very strong performance bias. So if you choose a solution that is primarily a property graph solution, perhaps there's an RDF connector, but it doesn't perform very well, or vice versa if you chose an RDF-based solution. So from that context, we built Amazon Neptune. And Amazon Neptune is designed for graph use cases that need to have very high throughput graph query answering with low latency. And to give you a sense, we think about two major classes of read operations. So we think about OLTP-based graph queries, which we define as parameterized graph traversals of less than 3 hops, or parameterized graph patterns. And for these kinds of OLTP traversals, Neptune's throughput is to support up to 10,000 OLTP queries per server per second with less than 50 milliseconds of latency. And then we support horizontal scaling through read replication with up to 15 different low latency read replicas. For the second class of queries, which we think of as OLAP queries, or complex reads, and we define them as parameterized traversals of 3 or more hops, on-bound graph patterns, combinations of those with complex filters. The target throughput is to support up to 100 per server per second, but the latencies will vary. And the latencies will vary from hundreds of milliseconds all the way up to minutes or more, because the ability to evaluate a complex read query very much depends on the shape of the data that you have underneath and how much data do you have to touch to evaluate that query. Now, complex reads, of course, have the same sort of horizontal scaling capabilities that you get for OLTP queries. So this is an overview of sort of Neptune's high-level architecture. The core of Neptune is this blue rectangle. So Neptune is a purpose-built storage engine that's optimized for processing graph queries. And it's durable and acid with immediate consistency. We support both the Tinkerpop and Gremlin stack, as well as the RDF-SPARKL stack. So every Neptune instance has a WebSocket server connection that you can use to connect any of your Tinkerpop Gremlin WebSocket clients, as well as a Gremlin REST API. We provide a REST interface that implements the SPARKL Protocol 1.1, which you can use with your RDF-SPARKL clients. And then we also provide some functionality for managing the database. So we provide a bulk load capability, which provides a fast, non-transactional, parallel bulk load for data that you have stored in S3. You can use this through the REST interface. You post JSON documents to the REST interface. These JSON documents specify load configuration. So they specify S3 bucket, IAM credentials, different properties. For property graphs, we support a CSV-based serialization, where nodes and node properties are serialized in one set of CSV files. And edge and edge properties are serialized in another set of CSV files. For RDF, we support 4 different RDF serializations. So we support N-triple, turtle, N-quads, and RDF XML graph serializations. In general, to get the best performance from the bulk loader, because it does use parallelism internally, we recommend having larger segment sizes of data in your S3 buckets. So typically, we recommend 200 megs or more to give you the best write throughput with using the bulk loader. We also provide some database management functionality. So We provide the ability to list and view running queries, the ability to cancel running queries. And all of this sits on top of a cloud-native storage layer, which was leveraged from technology originally developed for other instance-based database services at AWS. And I'm not going to go into this in too much detail because Bruce is going to really deep dive on it in just a moment. But this layer is what gives us our multi-AZ high availability, read replication. We support encryption at rest. And it's also enabled us to have a relatively fast path for things like compliance certification. So we achieved US HIPAA compliance at the end of August. So it's really a purpose-built database riding on a cloud-native storage layer that supports these open source and standard APIs. It's, of course, packaged as a fully managed service that has all of the things that you'd expect from AWS. So we have SDK and CLI support, so you can manage it completely via those mechanisms or via the console. We support CloudFormation. We support today encryption at rest, encryption in transit. You can manage your backup and restore functionality. So it's, as a fully managed graph database, it takes away that operational burden that you see as the graph databases grow and it becomes hard to maintain query performance. From a security perspective, Neptune supports deployment in virtual private cloud, so we only support VPC deployment. We support client encryption using HTTPs and TLS 1.2 for connecting to the Gremlin WebSocket clients or the REST endpoints. You can choose to use Amazon Key Management Service, or KMS, to use your own keys to manage to encrypt the data at rest. And you can also choose to enable IAM-based authentication. So you can choose to enable that for access to the Gremlin WebSocket or any of the REST services at AWS. It's just a quick flip of some of the customers that we had as public launch customers for this service. And today, we're generally available. We were announced in May. We were announced originally in 4 regions. We've expanded with 2 additional European regions. So we launched in London in October. We launched in Frankfurt this month. And then we're planning on continued region expansion. So with that, I'd like to turn it over to my colleague, Bruce McGaughey, to talk about our enterprise features.
Great. Thank you very much, Brad. I'm excited to be here and pleased to be able to share with you all some of what's under the hood of Neptune and show you how things work. So I'm going to be speaking about Neptune's distributed storage architecture and how we achieve performance, availability, and durability simultaneously with minimal trade-offs, all delivered as a managed service. So Neptune is built on a scale-out replica architecture. And by that, we mean that there's a primary engine node, which is servicing normally a dedicated write workload, although it can serve mixed or read workloads as well. It's built with a Gremlin and SPARKL endpoint, and they each have their respective query processing stacks. And those are built on a shared transaction management and caching layer for caching the pages out of the storage for in-memory query optimization. These engine nodes sit on top of a shared storage volume. To the engine nodes, it just appears as a sequence of 10 gigabyte segments. It's very easy to program and access to. In reality, under the hood, behind the network, there's a whole storage management layer that's hiding the fact that the data in the 10 gigabyte segments is actually striped across hundreds of storage nodes. And furthermore, those storage nodes are partitioned into 3 different AZs to guarantee availability, with 2 copies of every segment in each of the AZs. And the segments are distributed in a random manner, non-sequentially, across each of the AZs. That has a number of benefits, one of which is hotspot rebalance, which is very important for guaranteeing consistency of write throughput and read throughput. And hotspot rebalance is where one of the storage nodes may have some hot segments that are accessed by many of the engine nodes, so it's being overloaded on its network card. In that case, the management layer will automatically detect this overload and shift some of the segments to nearby storage nodes, which are under lower network load. And that's all possible because of the organization of the storage into 10 gigabyte segments and its striped nature. There's another important feature which we'll get into in quite a bit more detail, which is the ability for fast database recovery. So you can imagine, compared to striping this on a single disk, when you're restoring the volume at some point in time, we can parallel that work asynchronously across all these storage nodes. So we can do it much faster. There's another subtlety about Neptune's storage layer, and that is that the log application is actually embedded down in the storage layer rather than in the engine node, which is the case in many databases. So the engine nodes only have to ship the log down, and those are basically just containing the deltas that are happening on the pages rather than shipping full pages. So that massively reduces the amount of network traffic that the storage layer needs to handle, and for the primary for that matter as well. So that results in much less work on the engine for synchronizing with the storage layer, so the engine can stay focused on servicing the transactions in the transaction layer. It also minimizes network traffic. And after all, the network bandwidth is, at the end of the day, the bottleneck for read and write throughput. Another aspect and benefit of having six-way replication is the ability to survive an AZ +1 additional failure. And the way we do that is with the 6 copies across 3 availability zones, we work on a write quorum of 4 out of 6 and a read quorum of 3 out of 6. And indeed, in large fleets, it's possible to have all kinds of different failures. Disk and segment failures are common. You can lose an instance. You can even lose an entire AZ, either through loss of network connectivity or through losing power. And the reason we want to be able to survive AZ +1 is AZ events are relatively uncommon, but when they do happen, they tend to occur longer. So the likelihood that you have one additional, even just losing one segment, is relatively higher when you have a longer outage on an AZ. So we need to be able to survive those types of scenarios. So Neptune's storage layer is continuously monitoring for these kind of failures, and then it repairs itself by detecting missing segments. And through peer-to-peer gossiping, it rebuilds those missing segments on the fly automatically. So we have 2 scenarios here. On the left, we have a scenario where we've lost, with the small x, a disk or a segment of a disk. And in addition, that same segment is lost on 2 other instances where we lose the whole storage node. That's represented by the medium-sized x. So we've lost 3 of the segments. But with the other 3, we're still able to maintain read quorum and continue to operate the database. On the right-hand side, we have an example of losing entire AZ. And in this case, we can continue to service writes because we can maintain a write quorum of 4 out of 6. So still, we often get the question, why do we need 6 copies? There's actually 2 reasons for that. And one of the reasons, obviously, is availability. We just hit on that in the previous slide. So the question is, why wouldn't you just do 3 copies, 1 in each AZ? And the answer is, if you look at the upper portion of the slide, we lose AZ3 for a long period of time, represented by the lighter colored red dots. And then at some point where AZ3 is down, we lose, say, just a single segment on AZ1, then you'd lose your read quorum and be down for a period of time. On the other hand, if we have 2 copies in each AZ, when AZ3 goes down and we lose a single segment in AZ1, we can still maintain a read quorum of 3 out of 6. There's another equally important, if not more important, consequence of storing 6 copies of data. And it's a little bit counterintuitive. You might think, well, storing 6 copies of data is a lot of overhead. How would that help performance? The answer is that the performance is actually primarily driven by network latency. The engine nodes need to have acknowledgement from the storage layer that what they've written is durable, right? Well, network latencies have an exponential distribution. And indeed, in the tails of the exponential distribution, latencies can become intolerably long. So what the storage layer does is, instead of waiting for all 6 of the copies to be acknowledged, in the case of a read, it simply waits until 3. So the 3 longest latencies on the network are simply hidden by the storage layer. Similar thing happens with writes, where in a 4 out of 6 quorum, we can hide 2 of the longest network latencies. Another benefit of the distributed nature of Amazon storage layer is the ability to do continuous backup. And the way this works is every single of these segments is continuously being backed up in the background. Neptune takes snapshots of the segments, and because the segments are relatively small, Neptune can snapshot on a frequent basis. In the meantime, Neptune is shipping the redo logs in between segment snapshots over to S3, so they're durable there as well. When a restore happens, Neptune loads the nearest snapshot for each of the segments, and then begins applying the redo logs to catch up with the latest recovery point. So when Neptune does a restore in this manner, this all happens parallel and asynchronously. And it has an additional benefit, not just is backup parallel and fast, but when you need to recover, it's almost instant. So first, let's contrast how that would happen in more of a traditional database. In a traditional database, the data is maybe striped on one disk in a very bad case, or across a number of disks, but certainly not in a storage network layer like Neptune, at least in a traditional database. Typically, backup is achieved by doing checkpoints periodically, say every several minutes. When a restore happens, the database cannot be operational until all of the redo log has been applied, and that often is done in a single-threaded manner, so you can be down for several minutes. Neptune, on the other hand, has a little trick in the storage layer. The fact is that normal reads actually are following almost the same mechanism. So when you do a read in Neptune, the engine node requests a page from the storage layer. It's entirely possible in the storage layer that not all of the redo logs have been applied to the page yet. The Neptune will catch up on the fly and return the page. And this all happens really fast because the storage layer is composed of SSDs and very powerful storage nodes, so we can achieve that, and it actually ends up being a very small portion of the total latency of a request. Now, if you'll note that since Neptune can tolerate doing reads on pages where the redo logs have not yet been fully applied, then you'll see that we can actually begin crash recovery immediately. There's no reason to wait until the redo log is applied. We can just start operation immediately. There's another interesting feature that's quite useful, which is database backtrack. Because we have small segments and a history of them and can recover quickly, you can ask Neptune to simply rewind to some point in time, and that'll happen almost instantaneously. Furthermore, the rewind is non-destructive, so you can rewind a point in time, check the status of the database, rewind again, or even fast forward until you find the point in time where you are comfortable with the state of the database. So if you, for example, have some unintentional inserts or deletes, or an unintentional bulk load, or load the wrong data, or the wrong shape of the data, then you can just use this backtrack mechanism to go back to the point in time before the error occurred. Neptune's storage layer supports up to 64 terabyte volumes, and it's not really necessary to allocate up in front the amount of storage you intend to use. So Neptune auto-increments the storage in 10 gigabyte units and only allocates the amount that you actually need at any point in time. If Neptune detects that the storage volume needs to be grown, it's done automatically, and there's no impact on the performance. Similarly, from a user perspective, if you want to create a snapshot, in addition to the backups that are happening in the background, that's also done with no performance on impact because of the nature of the storage layer. So now let's take a closer look at the read replicas, which are the other side of the story for performance and availability. This story goes hand in hand with what's happening in the storage layer. So in addition to the Neptune primary, you can allocate up to 5 additional read replica instances. And these will work in synchronization with the Neptune primary to provide additional read throughput. And a very important factor is replica lag. And Neptune is able to provide very low replica lag relative to most databases, typically on the order of less than 10 milliseconds. The reason for that is because of the way the storage layer is architected. We're simply shipping redo logs, which are very minimal in size across the network, just the deltas instead of the full pages. Those same redo logs are shipped from primary to the replica. Because they're small in size, there's very little network traffic necessary for the replicas to stay in sync with the master. What happens, the replicas will check if any of the pages that are in its cache need redo logs applied as they come in, and then it'll do so and advance the read view to stay in sync with the master. If, on the other hand, the replica needs to get something that's not cached and fetch it out of the storage layer, those are automatically in sync with the master because they've already been committed to the storage layer. So that's the performance side of the story with read replicas. There's also an availability side, which is equally important. For availability, Neptune has a management layer that's continuously monitoring the health of the engine nodes. If it detects a problem with any of them, then it replaces them automatically. In the case of a primary, Neptune will choose a replica, and you're able to specify which replica and specify the failover order. And then it'll fail over in less than 60 seconds, and in fact, typically less than 30 seconds for a failover. And you can use this mechanism, actually, as a nice little feature to upgrade the primary. So if you want to have a more powerful instance because your workload is growing over time, you allocate a powerful replica, you warm it up, and then you specify it as the failover node. And then at a point in time you're choosing, say when traffic is very low, you simply force a failover, and then that replica, the more powerful replica, becomes the new primary. And that all happens in a very managed, automatic fashion. So finally, with all this complexity happening under the hood, it's important to be able to monitor and understand what's going on. So we provide AWS CloudTrail, which essentially logs all of the Neptune API calls to S3. We also provide event notification using SNS subscriptions via either AWS CLI or through the AWS SDK. And finally, we ship metrics to AWS CloudWatch constantly so you can understand what's happening in the storage layer, what's happening in the instance nodes, and how your Gremlin and SPARKL queries are performing. So that's all I have. And with that, I'll turn it back over to Brad to talk about how to get started.
Thank you, Bruce. So I know lots of you are already using graph databases. We have a bunch of different resources that you can use to learn more, to get started. And so I just wanted to flip through those very quickly. So in the last couple weeks, we have released 2 different blog posts on the AWS Database Blogs. And this is the start of a series that we're going to be doing about using graph databases. And what they've done is they started showing how to use Neptune in the context of using SageMaker Jupyter notebooks as a way to query and interactively view the data. And so there's examples there about just getting started. There's a second one that shows an example using a air routes data set, which is quite common for learning how to use Apache Tinkerpop Gremlin. And so this would be an option for you to take out. And for the discriminating slide viewer, you'll be able to see that this was done by one of our UK-based solutions architects with the visualized spelling there. So another way to get started is to use CloudFormation. So we, of course, support CloudFormation. This is actually a screenshot from our docs. You can use the designer, or you can get started right away launching the script. So this is a very easy way for you to get a Neptune instance started. The blogs that I talked about come with CloudFormation scripts that not only provision Neptune instances, but they also will provision your SageMaker Jupyter notebooks as well. Pictures. Another thing that you can do is we have several different GitHub repositories. And so we have a Amazon Neptune samples GitHub repository on the AWS or the AWS samples lab. And there's a number of different examples there. All of the source code with the blog post is available. We have an example about how to do collaborative filtering, which is a recommendation engine approach. We now, even since I've taken the screenshot in the last week, we've added new samples. So we now have one about how to use IMDb to find 6 degrees of Kevin Bacon, if you're interested in having fun with that, as well as an example about how to use Glue and Athena to take data that you have stored in S3, turn it into a format that you can ingest into Neptune and start working with it in that data set. And finally, we also have some tools that are available. So we have a separate GitHub repo in the AWS Labs repo that hosts currently a tool to convert GraphML, which is an XML-based serialization of graphs used for property graph, into the CSV format that Neptune uses. We also now have a Java program that will do a parallel export of a Neptune instance. So if you want to take all the data in your Neptune instance and export it, we have that. And then additionally, we have, this one has also been updated. We have an example about how to use Glue and use Glue to ETL data into Neptune. So there's lots of resources that are available, and we're continuously working to build more. And we'd really like to hear from you guys about what you'd like to see and how we can make it easier for you to work with Neptune. So with that, I'm going to take a few questions. One of our senior engineers, Mike Personic, is in the back here, and he has a microphone. So if anybody feels like they don't want to yell out, we have a microphone, so raise your hand. And before we do, I'm just going to flip this up to take a picture. This is my contact information and Bruce's contact information. And at the service team, we want to hear about how Neptune is working for you. We want to hear what you're doing with it. So do please feel free to reach out and let us know. So with that, let me go ahead and take a question over here on the right.
How close am I, if I think of Neptune as BlazeGraph implemented on top of the Aurora storage engine?
So the question was, how close am I if I think of Neptune as BlazeGraph implemented over the Aurora storage engine? You are standing next to Mike Personic and myself, who previously to AWS did work for BlazeGraph. And Neptune uses lots of different open source packages as part of it. That's part of the nature of supporting both Tinkerpop and RDF and SPARKL. But if you've ever operated a BlazeGraph instance at large scale, you'll notice some really important operational differences. And so there's lots of things that are unique to Neptune that make it a much more scalable and easier to operate solution. All right, in the front here.
Yeah. Okay, so you mentioned graph joins are slow on relational databases, right? But where do people get into trouble when they try to apply relational thinking to Neptune? Like, what kind of queries? Like, are they concurrent queries that you would have thought run in O of 1, but they don't? Are they, like, going back to your graduate student, look up that slide that you had? Are they, if you had a record of every student in history and you had 1 trillion students, connected in a sparse graph, like where do customers run into trouble? What do you recommend? Where do you draw the line, basically?
Yeah, so I think one thing that customers do when they move from a relational database into graph is they think a little bit too strictly about modeling their data from a schema perspective, and so they think about that a little bit more than they necessarily need to from a graph perspective. From a query side, it's really about how much data the query has to touch to evaluate it. So there's cases where, if you retrieve nodes where you have a relatively simple query, but you have to materialize large number of properties, there's really no way around the fact that you actually have to read that data off the storage layer. So those are cases where you'll see slower performance. And the others are cases where you'd see a large degree of fan out in your data. And so those can be managed, and you can take a look at them. But there's certainly cases that you can use to optimize. Let's see. Take one from this side.
Do you plan to support cipher at one point in time, or that is out of the question?
Yeah, so the question is, do we plan to support cipher? For those of you that don't know, cipher is a declarative graph query language over property graph that was originally developed by Neo4j. Today, we do not support cipher. We don't have firm plans to support cipher. We are very interested in declarative graph query over property graph in general. There are some ongoing initiatives both within the W3C as well as the GQL initiative that you may be familiar with
There is the open cipher.
And there is also open cipher, and there's a translator between cipher and Gremlin. So that is certainly an option, but as of today, we don't support cipher. I'll take one more from over here. I think in the...
Thank you. So what's the Neptune strategy for this multi-region replication? Like, does it support something like a multi-master, like what the DynamoDB has right now?
Yeah, so the question was, if I can paraphrase, is the Neptune storage layer something like DynamoDB's multi-master functionality? Yeah, so the Neptune storage layer is very different than DynamoDB's storage layer. In terms of multi-master functionality, it is something that we're thinking about on the Neptune roadmap, but it's much further along, most likely towards the end of next year time frame.
He was asking about cross-region replication too.
Yeah, so and we today do not support cross-region replication. We plan to support a cross-region backup and restore in most likely the first half of next year, and then we will support eventually multi-region replication, although again, that's in the further out timeline. All right, let me switch back over to this side just to make Mike run around as much as possible.
I was curious if you have plans on supporting geospatial types or GeoSparkl.
Yeah, so the question was, do we plan on supporting geospatial types or GeoSparkl? We have a lot of customers that are interested in geospatial and graph. I think our current thinking is that we'll support something like a z-index type of geospatial encoding initially, and then look at demand to support a full GeoSparkl implementation. As you're likely aware, GeoSparkl has lots of different aspects to it. All right, let me take one right over there.
What kind of learning curve are your customers experiencing when it comes to learning Gremlin? If they're relational developers, they're coming from SQL, they hit Gremlin. What kind of learning curve are you seeing, and are you doing anything other than some of the things that you showed to maybe shorten that learning curve for them?
Yeah, so I think one of the interesting things about Gremlin is that there are many, many ways to write different traversals in Gremlin, and they are effectively equivalent traversals, but they can have different performance characteristics. So that's something that people run into. We have one of our data architects is actually wrote the book on Gremlin about a practical guide to Gremlin. So we use that as a tool to help customers understand how to use it. Some of the blog posts and guides are sort of building out more examples in that area. So we're trying to both create more content that lets developers learn how to use Gremlin, as well as we're also interested in direct engagement. So if you have particular questions, we're happy to work with you about that.
I wanted to add to what Brad said. I mean, we've worked with customers in data labs where they've actually had the feedback after they get over the initial learning curve of Gremlin. They actually find it really a refreshing way to develop. They don't have to deal with all the schema and some of the things that go with relational.
All right, so we'll go back, try in the front, and then go ahead.
So how far away are you from giving users access to some of the Neptune logs so that can help them with debugging?
Yeah, so the question is, how far away are we from getting users access to the Neptune logs to help with debugging? We have a pretty strongly focused story on increasing transparency into the query engine. And so we've recently released support for query hints, which allow you to specify different hints to the optimizer to take on different patterns. We will be providing support for query explanations and query plans for you to take a look at what's the plans, or what are the plans that are being generated, and how can you then look at the plan and try and understand how to adjust your query. And then we're interested in feedback about sort of telemetry in general. So we've been improving the kinds of error messages that you get, for example, with IAM authentication, so that you can understand that it's that your credentials have expired and that's why you're getting an error, rather than something in general. So we definitely have a strong story and a focus on increasing transparency there, and we'd be very interested in feedback. So let me take in the back, in the black shirt.
Yes, we're working on a repeatable read, like snapshot view for transactions.
Okay. And how you recommend, you said there is no replication between regions. How you would recommend to deploy it across regions?
Yeah, so we have a couple different customers that are working on cross-region patterns. And they effectively fall into a couple different categories. So some customers are using DynamoDB global tables as their way to replicate data across regions, and then they're reading from those global tables to keep information in sync. Other customers are essentially bifurcating their ingestion and using that as the way that they replicate across regions. The cross-region backup restoration that I mentioned earlier, for use cases where the cross-region mode is for disaster recovery, that will help enable those kinds of use cases.
Are you recommending to use something like Kinesis streams in order to stream?
Yeah, you can. So you can use Kinesis. So in the model where you're bifurcating the ingestion, you can use Kinesis streams then to send that across to another region. I'll take the one right in front there.
I have two questions. One is, do we have a browser, like a Neo4j browser, from the developer perspective to debug something quickly?
Yeah, so today Neptune only provides the WebSocket and the REST endpoints. The Jupyter notebooks that I mentioned earlier are a step towards letting you sort of explore the data. We do plan to support...
Like I'm just asking from a graphical perspective.
Yeah, so we do plan to support an in-console query capability that lets you issue queries and see results in the data. Initially, that'll take the form of a sort of a tabular result set view, and then we'll also add a graphical view. We're trying to straddle the line between being a really fast, effective graph database that provides visualizations to help developers versus providing visualizations that you would use to build an application.
And have you guys tried using Tinkerpop Spark plugin to communicate with the Neptune database? Because I tried and there were some issues when I tried to download the open source.
We have had customers that have tried and reported it's successfully used. We haven't tried it ourselves, so we'd be happy to follow up and try and see what the gaps are.
Okay, thank you.
Sure.
Just to clarify something, I was in one of the workshops yesterday, and at least as I understood it, they said that sometimes Neptune can rewrite or change a little bit the traversal.
So the question...
On the Gremlin that you wrote, it might execute slightly different, like a query rewrite mechanism.
Yeah, so the question was, you attended a workshop and they were talking about the fact that you might execute a query and the actual query that was executed may be different than what you expressed in the Gremlin traversal. And that's absolutely correct. So Neptune is optimized and has a query optimizer for both the Gremlin and the SPARKL stack. And that's how what we use to get good performance out of the queries.
Okay, but basically you took an imperative query language and treated it as a declarative, as if you were able to rewrite it.
So we're definitely working on, it's a challenge for sure. So.
Thank you.
All right, let me go back to this side. Go ahead. Yeah, so the question is, are we supporting any object graph mapping frameworks? So actually, one of our partners who was here earlier has done some work to extend the Spring framework for Gremlin to work effectively with Neptune. So that's an option from the Gremlin side. And there are a couple of RDF options as well. So it's not something that we are directly supporting officially, but I know that lots of customers are interested in using object graph mapping type techniques. We have some customers that are looking at sort of migrating to Neptune from other solutions and porting through their object graph mapping layer.
There's a couple of them that are already working with the Tinkerpop, but sometimes we haven't had a good success with the Neptune importing just because of various.
I think please follow up with us on that, because I think we'd like to we can help you and we'd like to understand what the gaps are there.
Thank you.
Let's see. Go ahead in the front here.
So question is, when you have really one set of data and you're plotting a graph on one set of top data, seems pretty nice, right? As you add more entities, or you bringing data from some additional external entities and you have data quality issues, are you trying to integrate another graph solution into this graph itself? Have you thought through, like, what are the challenges that people come across, and how do we solve for those kind of issues, especially to do with the data quality itself, right? especially to do with the testing of data as we add more nodes or as we add more entities. That's what I mean, right? So,
Yeah, so the question was, if I can paraphrase and let me know if I'm incorrect. So one of the use cases for graph is to bring many different data sets together. And when you bring data sets together, they often have varying degrees of quality. And to use them in a production application, and you need to do quality control and make sure that your data is high quality. So there's a couple of different approaches that people use. Some people, which I've used sort of the more traditional relational approach, is they do it on the ETL process, and they'll do the quality control in terms of the validation on the ETL. Another approach that people on the graph side do is they'll import the data into the graph as is, and they'll use the graph to explore and try and understand where the quality gaps are, and then they'll make new versions of that data in the graph and use that as part of their application. In the back as well.
You mentioned earlier that the queries are efficient up to 3 hops. So in the example you gave from student to university part of back to methodology 3 hops. What's the limitation there? I mean, later you mentioned the 6 degrees of Kevin Bacon. So if you're only efficient up to 3 hops away,
Yeah, so it wasn't that we're not efficient up to 3 hops. Actually, I'm getting the signal that we should continue this discussion outside. So we'll be out and available to talk. So thank you very much.